Hello everyone, this is Kevin and Alvin, and we will be presenting our experiment to prove conservation of momentum. In order to prove conservation of momentum, we had to create a system that would be like a closed system, and one such that our objects that we were testing would maintain a constant velocity. We decided to use an air track and use the two sliding carts that came with the track. Two motion sensors, as well as cardboard pieces on the carts, were used to capture position, and a magnet was used to repel one cart, having it collide with the other cart at a point in the middle of the track. A needle on one cart, as well as clay on the other, allowed the two bodies to stick together and move down the track together, creating an inelastic collision.
The purpose of this experiment was to test the conservation of momentum for two-body collisions. In the absence of external forces, the momentum of a closed system is conserved. In an experiment, it might be difficult to eliminate external forces completely, but it is important to know that when internal forces of the system are much greater than external forces, momentum is still conserved. Well, this is because external forces will be very insignificant in that case. External forces are forces caused by external agents outside of the system. These can include but not limited to drag and gravity, depending on the situation. A closed system is one with no gain or loss of mass. For this experiment, it is important to know that momentum is a product of mass and velocity. In a two-body collision, conservation of momentum means that sum of momentum before collision equals to sum of momentum after collision. For this experiment, we are going to represent initial velocity with u and final velocity with v, and the masses of the two bodies colliding with m1 and m2. For this experiment, to be specific, we are going to deal with completely inelastic collision. We all know that there are two types of collisions. A collision can be either elastic or inelastic. With elastic collision, both momentum and kinetic energy are conserved. With inelastic collision, only momentum is conserved, but kinetic energy is not conserved. With completely inelastic collision, we expect the two bodies colliding to stick together. This is because maximum kinetic energy is lost. This energy is the one that is used to bind the two bodies together.
In order to get data values for our experiment, we had to analyze the points that Professor Rehagen gave us. After importing the comma-separated values into Logger Pro, we generated graphs using the points, having time being on the x-axis, then two distances measured from the carts to motion sensors for the y-axis. From the plots, we could see two different color lines that cross each other at around time equals 5 seconds. From observing the videos of Professor Rehagen releasing in carts on the air track, we can infer that around t equals 4.5 seconds, where the slope of the red graph begins to level off, and where the flat line of the orange graph starts to develop a negative slope, is the time where the two carts collided and attached and slid down the air track together. By creating a linear fit graph, we can generate the slopes, or the value m, of the graphs. The slope value of the bottom graph can be used for the initial velocity, named u in our calculations, while the slope value of the top graph can be used for the final velocity, which we used as v in our calculations. Here are our recorded values. We completed 12 trials. Our mean u value, or initial velocity, was roughly 0.231 meters per second, while our mean v value, or final velocity, was roughly 0.117 meters per second. Standard deviation for u was roughly 0.0154, while standard deviation for v was roughly 0.0095.
We now know that initial momentum P initial equals m1 u1. Final momentum P final equals m1 plus m2 multiplied by v. This implies that change in P equals m1 u1 minus m1 plus m2 v. m1 equals 0.216, m2 equals 0.2017, u1 equals 0.31, v equals 0.117. We also need the uncertainties in those variables. For M1, the uncertainty is 0.00005, and this is the same for M2. The uncertainty in U1, we can use the formula, the standard deviation in U1 values in the method section divided by n, the number of trials. In this case, we have n equals 12 trials. So our uncertainty in U1 equals plus or minus 0.004. Uncertainty in V, we use the same formula, the standard deviation in V divided by root n, where n is the number of trials. So the uncertainty in V equals 0.003. Now that we have everything we need to calculate momentum, we found out that P initial equals 0.009896. P final equals 0.0488709. Then the modulus of the change in momentum is equals to difference between P initial and P final, which happen to be 0.001. It's also necessary to find the kinetic energies. Initial kinetic energy is given by half m1u1 squared. Final kinetic energy is given by half m1 plus m2 v squared. We all know the values of the variables. So, substituting all the variables, we get total initial kinetic energy as 0.00576. Total final kinetic energy equals 0.00286. To find the change in kinetic energy, we say final kinetic energy minus initial kinetic energy, which is equal to 0.00290. And this number is just nothing but energy lost. It's also a necessity to find the error in change in momentum. To find the error in the change in momentum, we use the partial derivative method. Change in momentum equals m1u1 minus m1 plus m2 multiplied by v. If we apply the partial derivative method, we get the error in delta P as 0.002. To find the error in change in kinetic energy, we also use the partial derivative method. We now know that the change in kinetic energy equals to final kinetic energy minus initial kinetic energy. That is, kinetic energy equals half m1 plus m2 v squared minus half m1 u1 squared. If we substitute the values, the error in change in Ke equals to 0.0002. Now we have our values for change in momentum and the value in change in kinetic energy. The change in kinetic energy, therefore, is 0.001 plus or minus negative 0.002. Note that the uncertainty in a change in a P has got 3 decimal places. So the change in potential in a momentum value is supposed to be in 3 decimal places as well. Changing in kinetic energy equals 0.0029 plus or minus 0.0002. The error in change in kinetic energy is in 4 decimal places. So the change in kinetic energy value is supposed to be in 4 decimal places as well. We also know the amount of energy lost, that is the change in kinetic energy, and we have already calculated it, and we know the initial kinetic energy. So percentage energy lost will be given by energy lost, whatever the amount, divided by initial kinetic energy, which is equals to 50.3%. According to the results, momentum was conserved. The difference between the theoretical predictions and the measured results is less than the experimental uncertainty. Theoretically, we know that delta P equals 0. This is because P initial equals to P final. According to experimental results, delta P equals 0.001, which is less than the experimental uncertainty 0.002. The results also shows that there is significant amount of energy lost. 50% of the initial kinetic energy was lost. This is because most of the energy was used to bind the two bodies that collided together.
There were some sources of error that we did not account for, which affected the experiment. We did not account for drag force that the cardboard created while the cars were sliding towards the right. This is very hard to account for since it's very difficult to calculate the drag force the cardboard created at the specific moments of time that we collected data. The cardboard and Logger Pro may not have been aligned perfectly, which may cause some deviations in the distance readings. One way to fix this is to manually use straight edges in order to perfectly align the cardboard pieces as best as possible perpendicular to motion sensor. The system is also not perfectly closed, which would then cause the conservation momentum to be imperfect. One possibility to alleviate this is to create an environment with less confounding variables, potentially temperature or any air currents in the room. Lastly, the second cart appeared to drift away somewhat in a few of the videos that Professor Rehagen took. One way to fix this is to have another partner watch and prevent this from happening. Alright, so this is the end of our video. Hope you guys learned something and enjoyed it. Like, comment, and subscribe. Thank you.